Welcome to BIOL1026, Chemistry of Life, and welcome to the Chalk and Talk summary lectures of the course. This is the first lecture. We will talk about substitution. Okay? Basically what we will do is to study how we can make this reaction. Okay, we have here a carbon that is bonded to X, where X is a halogen, okay, and R1 to 3 is equal is a carbon chain or a hydrogen. Okay? Basically what we want to do is we add a nucleophile, and basically this nucleophile attacks the carbon and the halogen is departing, and what we get is basically the substitution of this nucleophile for the X. Okay? This is basically what we will do. Okay, first we will identify each part. That means X will be we will call it the leaving group. Okay? And normally the leaving group is always an atom that is more electronegative than not the carbon. That means that we have a density negative charge here, and the carbon has a density positive charge. Typical example, halogens. Okay, are more electronegative than not the carbons, and for this reason the halogen will have a density negative charge while the carbon will have a density positive charge. Then we can identify the nucleophile. The nucleophile is an atom or a molecule that has a pair of electrons and or a negative charge that can attack this carbon. Okay, this pair of electrons is attacking this carbon. Okay? Good. Then, when we define this, we can define how is happening this reaction. We have two options basically. Okay, the first option is that the nucleophile attacks at the same time, attacks or create the bond at the same time X is leaving. Okay? We form this bond at the same time that we are destroying this bond. Okay? How is happening? Okay? Here we have the molecule, and then the nucleophile attacks from behind, okay, just opposite where we have the carbon leaving group bond, okay, and what is happening is that basically you have the nucleophile in one side. This is like an umbrella. Basically, the free substituents are in my direction, but because the nucleophile is coming from here, are taking a planarity. This becomes planar, and then we will do an inversion of the configuration. Okay, what we have. And we are destroying, or we are breaking this bond, the carbon halogen bond. Okay, R1, R2, and R3 are all in one plane in the transition state that is perpendicular to the plane of the whiteboard. Okay, and importantly, as I said, this is a transition state. Okay? What is happening is that the nucleophile attacks at the same time that the leaving group is departing, or we're breaking the bond between the carbon and the halogen, or the leaving group, and then what we get is the final product. With inversion of the configuration. What means inversion of the configuration? Well, what we can do is to put an example. We will put a chiral center. Okay, we have this compound that has a methyl, a hydrogen, an ethyl, and an iodide. Iodide is the halogen, and the iodide will be the leaving group. Okay? And then as a nucleophile, we will use, for example, sodium methoxide. A very good nucleophile. Okay, what is happening? Well, if the substitution takes place, this is forming the bond at the same time that the leaving group is departing, what we will get is a text here, and this. We are forming this bond between the methoxide and the carbon at the same time that we are breaking this bond. That means if we grow the transition state, this reaction has transition state. Okay, what we will have is the methoxide that is forming the bond with the carbon. Okay, this ethyl is up. Okay, we are inverting the configuration. This is coming from here. That means that this is like an umbrella. Okay, that means that we will put now planar, hydrogen inside, the metal here. This is a planar. This is in a plane perpendicular to the whiteboard, and we are destroying the carbon halogen bond, carbon iodide bond now. Okay, this is a transition state, and then simply this bond is formed, this bond is broken, and what we have is methyl and ethyl and check that what we did is that now the hydrogen and the methyl and the ethyl that are in this direction now are in the opposite direction. We have an inversion of configuration. Okay? This is the most important. We have the reaction forming the bond between the nucleophile and the carbon at the same time that we are breaking this bond. We form this transition state, and then we get an inversion of configuration. Okay? Then, how is called this reaction? This reaction is called nucleophilic substitution bimolecular. Okay? Why is called nucleophilic substitution bimolecular? Nucleophilic because with the addition of a nucleophile, substitution because we substitute a halogen or a good living group for a nucleophile, and bimolecular because if we check the rate determining step of the reaction, as you can see here, which will be the rate determining step? Well, will be from here because it's only one step. Okay? The rate of the reaction will depend on the concentration of the nucleophile and the concentration of the molecule that is reacting. Okay? Because both compounds are acting as participation in the rate determining step. Okay? This is the nucleophilic substitution bimolecular. But when we are doing this type of reactions, we have some other options, yes. We can have another option. What it is? Well, the other option that we can do a reaction is basically what could happen is that the living group is departing, okay? And what we generate is a carbocation. If this pair of electrons that are forming the carbon X bond is taken by X, we have okay? The living group is departing first, and then what is happening is that the nucleophile, once we form the carbocation, the nucleophile attacks the carbocation, and what we get is we get the final compound. Okay? What is the main difference? Well, the main difference is that in this reaction, the living group is departing first, we generate a carbocation, and this carbocation is an intermediate. Okay? And then, after we form the carbocation, the nucleophile attacks the carbocation to form the final compound. That means that we have two steps. This is the first step, and this is the second. Okay? Important things that you have to remember. One is that the carbocation, because it's a carbocation, is a planar. Okay? That means we have phyroid perpendicular to the slide, the whiteboard. What I have, this is the planar carbocation, okay, this is the sp2 hybridization, and this is the pz orbital, okay? The pz orbital that is perpendicular to the plane of the carbocation. Why this this is important because if the carbocation is planar, okay, I draw it in a different way now. Okay, this is the carbocation. The nucleophile can attack for this phase or can attack for this phase. Whatever phase is okay, because this is planar. That means that if we have a chiral compound, if we do this type of reaction, what we will get is a racemic compound. Because basically when we have the carbocation, the nucleophile can attack for both phases of the carbocation. Okay? How is called this reaction? Well, this reaction is called nucleophilic substitution unimolecular. Why? Well, we have to check the rate determining step. The rate determining step is the first step. Okay? The difficult reaction is to form the carbocation. If we form the carbocation, after everything is going fast. That means that this is the rate determining step. This is the difficult reaction. Which compound participates in the rate determining step? Only this compound. That means the rate determining step, the rate of the reaction will only participate by this compound. Only by the concentration of this compound. Okay? This is why we only call it unimolecular. Okay? What is the important point? What is the most important point of this? Basically, the most important point is that we form the carbocation. This carbocation has to be stable. This is our leitmotif to do this reaction. Okay? That means we explained the nucleophilic substitution bimolecular. We form a transition state, we have an inversion of configuration. These will be the two most crucial characteristics of the SN2. And in the SN1, the most important characteristic is that we have a carbocation, and this carbocation, because it's planar, the nucleophile will attack by both phases. We will get a racemic compound if the starting material is chiral. Okay? What you need to know is which is the mechanism, how are going the arrows in the nucleophilic substitution bimolecular. Remember, we form the nucleophile carbon bond at the same time that we are breaking the carbon halogen bond, and in the case of the nucleophilic substitution unimolecular, first step, the leaving group is departing. We form a carbocation that is an intermediate. Next step, nucleophile attacks to the carbocation to form the final compound. Okay? Good. Then, the question that we have now is how we can differentiate when a reaction is a SN1 and when a reaction is a SN2. Well, the thing that we need to do is to check the starting material. Okay, the starting material, remember, is this. Okay? We can have three different situations. That R1 is equal to R2 is equal to R3 and is a hydrogen. R1 is equal to R2 and is a hydrogen. R3. R1 is a hydrogen, or R1 is equal R2 is equal R3 and R not hydrogens. Okay, these are the four options that we have. In the first case, we can have three hydrogens. Okay, R1, R2, and R3 are all hydrogens. Second case, we have two hydrogens. Third case, we have one hydrogen, and in the last case, we have zero hydrogens. Okay? Then we have to analyze which is the mechanism. In the SN1, what is happening? We have to form the carbocation. Our objective is to form this carbocation. Okay, this is the objective of the SN1. This is the crucial point. When will be easier to form a carbocation? We know that the stability of the carbocations is depending of how are the substituents. When more carbon substituents we have, more stable is the carbocation. That means, in this case, with three hydrogens, no stable carbocation. Okay? Why? Because three hydrogens are not stabilizing the positive charge. When we have two hydrogens, is slightly more stable than not three hydrogens, but it's not enough. If we only have one carbon chain, it's not enough to stabilize the carbocation. If we have only one hydrogen, this is more or less stable, and with zero hydrogens, it's very stable. Okay? Then we analyze the reaction of substitution, nucleophilic substitution bimolecular. What is the key of the nucleophilic substitution of bimolecular? Is that the nucleophile is forming the bond at the same time that the leaving group is departing, or we are breaking this bond. We form this bond between the nucleophile and the carbon at the same time that we are breaking the carbon-halogen bond. Okay, this is the key. Then, what is important? Well, the nucleophile has to arrive to do the bond. Okay, the pair of electrons of the nucleophile has to arrive to the carbon. Then, if we have three hydrogens, are very small, that means that will be no difficulty to do it. If we have two hydrogens, will be more difficult than not three hydrogens, but also will be possible. If we have two groups here and only one hydrogen, a carbon will be always be bigger than not a hydrogen, this will be quite difficult. And if we have three different substituents that are not hydrogens, this will be impossible. That means, if we have a compound with zero hydrogens, the only possibility is SN1. If we have a compound that has three hydrogens, the only possibility is SN2. If we have two hydrogens, the only possibility, in the major part of the cases, remember that always there are exceptions, but in the major part of the cases will be SN2. While when we have one hydrogen, we don't know. Could be SN1 or could be SN2. There are points for the SN1, there are points in favor of the SN2. Okay? Remember that I will never ask, in the case of one hydrogen,